Consider the pervasive challenge of extracting reliable insights from complex observational data. While ordinary least squares, or OLS, stands as a foundational method for regression analysis, its efficacy is fundamentally tied to stringent underlying assumptions. Real-world datasets rarely conform to these idealized conditions, often leading to misleading inferences and suboptimal predictive models. The robustness of OLS hinges on critical assumptions, linearity in parameters, independence of observations, homoscedasticity of residuals, and normality of errors. When these are violated, particularly homoscedasticity, OLS estimators become inefficient. This impacts the precision of estimates, even if unbiased, making them less reliable for drawing conclusions. Heteroscedasticity, where the variance of error terms is not constant across independent variable levels, does not bias OLS coefficient estimates. However, it renders them inefficient, lacking the smallest possible variance. Crucially, standard errors become inconsistent, leading to incorrect p-values and confidence intervals, thereby invalidating hypothesis tests and potentially misguiding policy. To address the inefficiency caused by heteroscedasticity, weighted least squares, or WLS, provides a robust alternative. WLS minimizes a weighted sum of squared residuals, assigning smaller weights to observations with larger error variances and larger weights to observations with smaller error variances. This effectively downplays less precise data. Implementing WLS necessitates an accurate estimation of the error variance structure, often the most challenging aspect. This involves modeling the variance function, perhaps as a polynomial, or through iterative reweighting. Initial OLS residuals estimate weights, then the model is re-estimated. The precision of WLS hinges directly on the fidelity of these estimated weights, demanding careful diagnostic checking. While WLS resolves issues related to error variance, a different, equally insidious problem can plague regression: multicollinearity. This occurs when two or more predictor variables are highly correlated with each other, rather than primarily with the response. This internal correlation among predictors introduces significant instability. Multicollinearity inflates the variance of OLS coefficient estimates, making them highly sensitive to minor data changes, often leading to illogical signs or magnitudes. It obscures individual predictor contributions, making interpretation unreliable and hypothesis tests misleading. The Variance Inflation Factor, or VIF, quantifies this increase. A VIF exceeding 10 often signals problematic multicollinearity, requiring intervention. Addressing multicollinearity requires careful consideration. Strategies include removing a highly correlated predictor if justified, combining them into a single composite variable, or employing regularization techniques such as ridge regression. Ridge regression adds a penalty to the sum of squared coefficients, shrinking their magnitude and reducing variance at the cost of a small, controlled bias, thus stabilizing estimates. Beyond error variance and predictor correlation, many datasets possess inherent hierarchical or clustered structure. Traditional OLS models implicitly assume all observations are independent. However, in longitudinal studies, nested experiments, or meta-analyses, this assumption is fundamentally violated, leading to underestimated standard errors, inefficient estimates, and potentially spurious significance. Mixed models, also known as multilevel models, offer a robust framework for analyzing structured data by explicitly accounting for dependency. They incorporate fixed effects, representing population-level average effects, and random effects, accounting for subject-specific or group-specific variations around these averages. For example, in a patient recovery study across hospitals, drug efficacy is fixed, while hospital-level recovery variation is a random effect. The primary advantage of mixed models lies in correctly partitioning variance components, distinguishing between within-group and between-group variability. This allows for more accurate standard errors, more powerful hypothesis tests for fixed effects, and the capacity to model heterogeneity in effects across groups without violating independence. They provide richer insights, leading to more nuanced and valid conclusions. Despite their power, mixed models introduce complexities. Specifying the appropriate random effects structure, determining the optimal covariance matrix, and handling convergence issues all require careful model selection and validation. Computational demands can also increase significantly with large datasets and intricate random effects designs, necessitating advanced software and robust estimation algorithms for stable results. Mastery of advanced regression is not about choosing one method in isolation, but understanding when and how to apply each within a comprehensive analytical framework. The workflow begins with meticulous diagnostic scrutiny, identifying heteroscedasticity, detecting multicollinearity, or recognizing hierarchical data structures. Only after a thorough diagnostic phase can the appropriate advanced method, be it WLS, Ridge Regression, or a mixed model, be judiciously applied to ensure valid, efficient, and reliable inference. Ultimately, moving beyond basic OLS regression involves a deeper appreciation for the nuanced properties and pitfalls of real-world data. By actively addressing violations of classical assumptions and rigorously accounting for complex data structures, analysts significantly enhance the reliability, precision, and interpretability of their statistical models. This informed approach transforms regression into a powerful instrument for uncovering true underlying relationships, leading to more robust scientific discovery and profoundly informed decision-making.